And that brings me to the last topic of this unit on proof techniques, and that's about correctness proofs. So in this case, we want to show something about programs, about algorithms, and we want to show that they're correct. Now, what does correct mean? So I mentioned before that there's a whole field of formal verification that shows that tries to show that a program computes exactly what is desired. It's not our focus here, but we will informally use some of the techniques to reason about algorithms, because after all, an algorithm is not very useful if it computes some random nonsense. We want to be sure that it computes the correct thing before we accept it as a good and efficient algorithm. For formal verification, you have to specify exactly what it means for your program to be correct. And that's usually two distinct things. First, we want to prove that the program eventually terminates. So whenever you give it a valid input, it should eventually finish. Now that sounds obvious, but a program can run into an infinite loop or an infinite recursion, and you might not really know what's going on. It's just very slow, and it keeps going, and you don't know whether it will ever finish, or whether it will just whether it will take a very long time, or it will run forever indefinitely. And the second thing is we want that if the program terminates, it usually produces some output, and we want that to be the right value. That makes a little more sense if we go to specific problems. But that's the usual two things that we're concerned with. Now, for proving termination, I will formulate this here for a recursive procedure. So you have some procedure that calls itself again, and it has different parameters. And we want to show that at some point this recursion stops. A way to do it is to define a potential function. That's something intuitively that becomes smaller with each recursive call. That's formulated here, but I'll come to that in a second. And that has to be a natural number. That's important. And well, that's at least 0 by definition, because a natural number is only starting with 0. So that's some function you compute based on the parameters that this procedure is called with. The second step we have to prove is that whenever we have a recursive call, we have to look at the code that implements this function. And if there's a recursive call to this same function, procedure again, it will have some other parameters, and they will somehow depend on the initial input. And we have to prove that whenever we do a recursive call, we get strictly smaller in terms of this potential. And that means eventually this procedure has to terminate, because we can only strictly decrease. So that means it's at least, but that's the same as saying this is less than these minus 1. And we can subtract minus 1 from a given number that we start with only a finite number of times. A similar idea can be made for loops. If you have a while loop instead of a recursive call, the two things are actually fairly similar. And you will see an example of this in the tutorials where you apply this to a loop to show that it terminates. On the second part, proving that the output is correct, I want to show you one specific technique that often helps for that. And that's called a loop invariant. So here the setup is there's a certain condition that we know, that we assume is true before the code runs. That could be something like the input is valid. Our list of numbers, we're given a list of numbers, and they're all integer numbers. sorry, that's the precondition. That's A. That's something that holds before the loop. And then the post condition is what we would want to hold after the loop. For example, it could mean that the input is sorted. I will show you a concrete example for this proof. But keeping an eye on the time, I would probably postpone that to the next session. But I'll explain the setup here, and then the concrete example will follow. So to prove that the post condition holds after the execution of the loop is our goal. And we might have a precondition that's true before the loop. And then there's a certain strategy how you can do this. And it basically means you have to look at specific points in the code before the loop and after the loop, but also the first thing inside the loop and the last thing at the end of the loop body. And then you have to find what's called a loop invariant. That is a statement, a logical statement about the variables in your code that has the following properties. The invariant is true at A before we enter the loop. The invariant is true when we, it's true at A, and if we enter the loop, then the loop condition is also true. So at the beginning of the while loop, we always have this. So we can assume I and the condition hold at B, and we want to show that this implies, again, that the invariant holds at C, at the end of the body of the loop. And finally, if we left the loop, we know condition can no longer be true, because otherwise we would have jumped into the loop again. So at position D, we know we want to have that the loop invariant and the negation of the while condition together imply the post condition that we are interested in. I realize this is fairly abstract, and it might be a bit detached from your experience, but once we go through the concrete example, I think it will become much clearer. And again, it's just a recipe how you can structure these proofs. The creative and tough part is still to find the correct loop invariant.